All right, so Unit 3 problems. Unit 3, check your understanding questions. So first problem, we want to know the correct expression for the heat transfer rate from node M plus 1 N to node M N. Oh boy, that's hard to say. So this you just need to use your Fourier's law. Make sure that you pay attention to what that area is, right? For this one, the area is delta y times the unit vector into the screen there. And so it's option B. Question 2, finite difference grid for a two-dimensional conduction problem with a control volume is shown. What's the correct expression for the sum of the heat flows into that node? And so this is all four coming from the neighboring node, and so this one is option B. Question 3, now we want to know the expression for the heat transfer rate from node Mn plus 1 to node Mn. So that's coming from the north up there. And again, this is Fourier's law. It's just making sure to keep what that area is, keep that straight. So that's option A. Question 4. Now we're coming from the south again. Using Fourier's law, figure out what that area actually represents. For this one, it's delta x times the unit vector z into the page there, into the screen. All right, question 6. So this gets into the lumped capacitance transient stuff. Small copper ball, initially at a room temperature, is dropped into a large pool of hot water. The copper ball stays submerged and never touches the pool boundaries. The graph that best describes the temperature of the copper ball as a function of time is. Well, first of all, we can go ahead and rule out B and C because that copper ball is never going to get hotter than its surroundings. We can't violate the second law of thermodynamics. It's not A, right? Because copper has very high thermal conductivity. It's not going to, you're not going to dunk it in there and it's going to stay at the same temperature and then start going up. No, it's going to be C. C is, and besides, if you looked at those equations for lumped capacitance, it's an exponential function, right? So C is absolutely, definitely the right answer. The Biot number is defined as HL over K. The physical meaning of the Biot number in terms of thermal resistances is that the term blank is related to the external resistance and the term blank is related to the internal resistance. And so we can reason out which one it is, and I've got some reasoning here. So it's 1 over H, which is the related to the external resistance, and you don't even have to think further than Ohm's law. So Ohm's law says the thermal resistance to convection is 1 over HA, right? We just kind of eliminated the A here because that Biot number, the A just gets divided out. But 1 over H is the convective resistance term, and then remember Ohm's law, and I think I've got it somewhere over here. Yeah, right there. So our thermal resistance to convection, 1 over HA, thermal resistance to conduction, L over KA. When we divide each of those resistances, the thermal resistance to conduction by the resistance to convection, of course, that area cancels out. So for the conduction portion of it, the internal resistance, it's L over K. All right. So let's move on to question 7. Cold metal object is put into a tank of hot water based on the lumped capacitance method. If the mass were decreased, the time that it would take for the object to rise to a given temperature would. So let's see. So if we take that lumped capacitance method or equation and we solve for time, we can see that as that mass it decreases, so does the time. Time decreases as well. A hot metal sphere placed into a cold water, so same thing. And this is phrased a little bit strangely, but it says if the thermal capacitance of the sphere were increased. And what they mean by thermal capacitance is the ability of that material to store, right? Just like a capacitor, right? Electric capacitor. So ability to store thermal energy without raising its temperature, and that's related to that specific heat. The thermal time constant that they refer to is the dimensionless time, it's the Fourier number. So again, taking that lumped capacitance equation, solving for T, and then getting that T in terms of the Fourier number. So T is the Fourier number, and T is the Fourier number times the characteristic length over the thermal diffusivity. And so you can see as that specific heat would increase, the Fourier number would also increase. So a little bit of roundabout reasoning, but yeah. All right, question 9. A hot metal sphere is put into a tank of cold water. So this is kind of similar to the previous, I guess, question 5. Um, yeah, a couple of questions ago where we were asking about the temperature, how the temperature changes. It's not A because you'll see that little arrow goes to infinity, like you have this infinitely large Q. Well, you're not talking about dunking it into a tank of cold water where there is an infinite temperature difference between the temperature of the water and the temperature of the sphere. So that's why A is not correct. It's not B either, because this would be the case if you had a steady state one-dimensional problem, because that delta T remained constant. Well, that's not the case, right? As time goes on, that delta T between the metal sphere and its environment is continuing to decrease, and so is that Q. So it's actually part C. And this is not question 1. Remember question 1? I think it was question 5 actually. But the temperature of that sphere, it's not changing in a linear fashion, it's changing in an exponential fashion. So it's C. Question 10, the important factors in determining whether the lumped capacitance method is valid for a given problem, such as the cooling of a solid in a liquid, are, and we select all that apply. So the object is made of a high thermal conductivity substance, such as a metal. Yep. Temperature gradients inside the object are negligible. Yep. The fluid is air or water at a low velocity. The conduction resistance inside the object is small relative to the convection resistance on the surface of the object. And so that kind of goes back to that Biot number, about the ratio of thermal resistance to conduction versus convection. So it's 1, 2, and 4. Okay. Next one, question 11. The validity, or the criterion for the validity of the lumped capacitance model based on the Biot number, is that the Biot number is, well, of course, it's got to be a lot less than 1, and we give a cutoff in this class of 0.1. Question 12. Temperature profile through a wall at an instant in time. So maybe this is a non-steady state problem, but we have a snapshot in time. The correct statement about the heat flow at the left face of the wall at x equals 0 is, well, it's going to be the first one because Q is going to be going in the negative direction, in the direction of decreasing temperature. The transient temperature profile at an instant in time is shown. So we have the temperature profile, right? How temperature is changing with respect to x. In addition to that temperature gradient, which we have, the additional information needed to determine the heat flux at position x is, and this just goes back to Fourier's law. So the only thing that you need in addition to that dt dx is, of course, your thermal conductivity. A plain wall is at uniform temperature and suddenly exposed to cold water on both sides. The lumped capacitance model is not applicable. If the thermal conductivity of the wall were increased, the rate at which the centerline temperature decreases would, well, that makes sense, right? Higher K, less resistance to conduction. It's gonna, right, heat is going to be transferred much more quickly. So, of course, the centerline temperature is going to decrease, coming in, faster heat transfer rate, the faster this that center line temperature tries to come into equilibrium with the environment around it. Question 15, same scenario, but now we're looking at the thermal diffusivity. If that were increased, the rate at which the center line temperature drops would, well, it's also going to increase because this is related to K, right? But it's also related to that specific heat. So that thermal diffusivity is going to increase as CP decreases, meaning that as that CP decreases, it has less of an ability to store thermal energy without changing its without changing temperature. All right, question 16, very last one. Cylinder and a sphere have the same diameter, thermal properties, and external convection coefficient. Both are at the same temperature. For a sudden drop in ambient temperature, the centerline temperature of the cylinder will decrease at. And so, again, I'm pulling out that lumped capacitance equation. And if I solve for T and I look at the ratio of volume to surface area, because that's really what would be different between that cylinder and a sphere, that ratio of the volume to the surface area for a cylinder is much, much large. Well, not much large, much, much larger. Just it's larger than for a cylinder rather than for a sphere. And so the time is going to increase. The heat transfer rate will is going to be lower, right? Um, and yeah, so you're going to be looking at a higher T for that. Okay, well I think that's it. And when I realize my head's in the way, so hopefully, yeah, there we go. Hopefully you got it now. All right, good luck on your test, and I'll see you Monday.